Ideal gas law, some of you guys might be familiar with it. It basically stands for pressure times volume equals a gas constant times temperature. So theoretically, if I lower temperature on one side of the equation, I would likely have to lower the volume or the pressure in that case on the other side of the equation to keep it balanced. So if I have a balloon, which basically is filled with air and sealed, and my lovely assistant is helping. All right, so what happens if I dip the balloon in it?
Go pop.
Maybe, maybe not. What else? Anybody else?
Look
Look at the ideal gas law. What am I doing?
It's going to shrink.
It's going to contract.
I'm lowering the temperature.
It's going to shrink.
So Bob says it'll contract. If he's right, I should be able to fit a decent amount of these balloons in here, I assume, right? Assuming he's right. So far he's right. So why is it contracting? What's happening?
This is the Bob Hague balloon.
Funny story. You did it, not me. So yeah, we're lowering the volume, but what are we literally doing to the air inside?
Shrinking.
Shrinking? What are we doing to the molecules of air?
Compressing them.
Compressing them, correct. We're making the molecules of air closer together right now. And by doing that, you literally lower the volume. But so that more. Actually, that's good.
You could be liquefying the air in the balloon too.
So you theoretically could if you left it in for long enough. I'm not going to do that here, but what happens when I take the balloon back out? It has to expand, correct? Did I take any of the air out of the balloon at all?
No.
Good. That's ideal gas law. Unless we break the actual surface of the balloon, we can't remove any of the air. All we do is compress it. So obviously air is a compressible quote-unquote fluid, just by proving that.
And then you can use it for, like to move a piston too, right?
Theoretically, yeah, obviously it vaporizes very quickly and expands very fast, so you can actually put a tremendous amount of pressure on a piston, make a rocket, make a bomb, anything like that.
I like the bomb.
Same principle, still ideal gas law. Chris has made a ping pong ball here, and what he's done is he's actually poked one small hole in it, made it basically tangential to the ball itself. So you got to think about the same principle we just talked about and tell me what you think is going to happen as soon as I dip this ball in the liquid itself. Think about, there's obviously the ball's filled with air right now, right? Theoretically. What happens to the air inside the ball? This ball is incompressible now, the balloon's compressible.
It's got a hole in it.
Yeah, it's got a hole in it, so what's happening right now, right, as it's submerged with the air in the ball? Think of the balloon. I'm not going to answer it for you. Not necessarily. The air itself is compressing right now because it's getting cold, which is what happens with the balloon itself. The ping pong ball is not compressing it, so not air is going inside. What's going inside? What's around the ball right now? Liquid nitrogen. So liquid nitrogen is going inside the ball right now because we're creating a vacuum, literally creating a vacuum inside the ping pong ball. To create a vacuum, it sucks the liquid nitrogen in.
It's going to steam just like the...
Yep. So what happens when I take it back out? I raise it to release it.
We all put our safety glasses on.
Safety glasses, please.
This is a safety carnival.
It's unpredictable. And Bob, if you wouldn't mind just tucking your legs in, I'm going to come around.
Oh, it's like a rocket. It's so freaking big.
So that's a really small amount of liquid that makes it go that fast. Sometimes it levitates, sometimes it explodes. It's the safety glasses. Just to give you the idea, it's still spinning. Tremendous amount of force.
How
Tremendous.
fast is that going?
Who knows, RPM wise. I mean, that thing went so fast, sometimes you can't even see the markings on it.
Do it again.
It also makes noise too sometimes. Can we grab some salt, Bob?
Yeah,
Can we
sure.
chop membrane or something like that? Chef here.
This is the inverse
like
of
1100
cooking. This is anti-cooking.
Anti-cooking.
It's a mountain house.
This is like a good...
Ooh, one-handed, nice. Yeah.
This is your brain.
Put that down for me.
Oh.
Shouldn't do it,
Who's going to eat that?
Drink, drink, drink.
What's happened in there now?
We're still on.
Better freeze.
Should be
You
hydrated.
see the yolk jumping around in that before it
First
goes
thing's going. This one's better without the yolk broken.
Oh, it's much better. It's pretty cool.
It's cooking.
Yeah.
Yeah.
Little hot sauce.
Not in this case. A little bit. I mean, obviously it's table season, so it is boiling. It's ready for it. I'm allowing it to expand. If I didn't allow it to expand, it would generate heat, of course, right? Molecules are staying against each other, vibrating faster, and generate heat.
Mikey, can you eat it?
So then,
Not that, no. I promise you. If you volunteer, you'll volunteer.
it's, you know what? It's sunny side up.
All right, next slide. So some of you guys have heard of superconductors before, maybe. We actually have a superconductor right here. What we're going to do is, if you look at this chart, talk about superconducting. In this case, we're talking about high temperature superconductors that occur above 30 Kelvin. They used to have much lower temperature superconductors that work with liquid helium. It cost way too much money to operate that. We now have ones that operate with liquid nitrogen and warmer. We have one here. It's yttrium, barium, copper oxide. This little black disc right here. It's just a ceramic disc. We have a rare earth neodymium magnet, really small cube, and at room temperature, these guys have no interaction with each other. It's actually the left side of that graph. Nothing really going on. So the point here is we actually can cool this down below that critical temperature and literally create a superconductor. And I am going to ask that you guys get up for this one if you want to be close to see this. Please don't touch the paint. That would suck. So what's that noise?
Vaporizing.
Yep, vaporizing. It's literally boiling before your eyes. Again, the room is very hot compared to that. So we're bringing that YBCO ceramic down below that critical temperature, just with liquid nitrogen.
It's gonna flow.
Why? You're right. The right side of that graph. That's the Meissner effect.
The magnetic.
Below that temperature,
It'll maglev.
yeah, it's going to be a maglev, literally. The magnetic field from this rare earth magnet below this certain temperature actually repels off of the ceramic disc, and it kind of forms an envelope. And not only does it repel, but it holds it in to the X plane. So Y gets repelled this way, if you want to call this Y, and X, it actually holds it into this field. So theoretically, I should be able to get this to levitate. Good to go. And I should be able to get it to spin. There you go. Now you guys can come in as close as you want to see this.
That's a better.
Now, theoretically, it's spinning right now, right? What happens if I do that in a vacuum? What I just did? Spin forever, perpetual motion. Why is it going to eventually stop here? Air resistance. We have no other resistance here. We only have air resistance. Obviously, with a train on a train tracks, you have physical friction. Well, that's the biggest resistance with a train. You start making maglev trains or trains that operate on superconductor, the only thing stopping them is air. So that's why they're shaped as a bullet, and they literally float on air when you're in them at 300 miles an hour. And this is what they're doing now. It used to be just electromagnets, but now they're actually superconducting magnets. So obviously if this gets above the critical temperature, which it will in probably about 5 minutes or so, that will drop and it'll become useless to us. I think we can make those YBCOs here. Now press. It'd be cool to make bigger ones. Get a bigger neodymium magnet. But that's a superconductor in essence. And the reason it's called superconductor is what you do is you lower the temperature so much, you create an amazing conductor. You lower the electrical resistance. Theoretically, you can run liquid nitrogen in electrical lines and have electrical current travel for hundreds, if not thousands of miles without losing its resistance or without losing its strength if you do it this way.
Could you make like a skateboard?
You can make a Back to the Future 2 hoverboard, theoretically, as long as you're hovering on a ceramic with a neodymium skateboard. Think about that. No, you can pretty cheap. Considering that's $90 just for those two, it'd be pretty cheap. That's a superconductor.
Back in the late 80s.